Hello. So in this section, in this video, we're going to start to look at the idea of a mathematical proof. So how do we prove things in maths? Okay. So in this video, there's going to be two subchapters about proofs. Well, actually, there's another one in year 13, but for AS 7.4 and 7.5, we'll be looking at proofs. But in this video, we're just going to talk about the idea of a proof, and in the next video, we're going to look at different types of proof. Now, okay, so types of proof then. Well, not types of proof, but mathematical proof. So, essentially, the core idea of a mathematical proof is we start with a known statement or a known fact, okay? A known mathematical fact. Okay, so that could be, for example, I don't know, we might need to use that 2 is an even number, something like that, and then prove, I don't know, that 2 squared is even, or something like that. I don't know, but we start with a known fact, and you'll see examples of what I mean by this when we look at examples in a second. So start with a known fact, and the idea is we want to prove some other statement, right? A statement that we don't know is true, but we want to prove it is true. So we start with something that is true, and then we start to then do more maths. So we basically do more steps, more mathematics. Then we obviously do some maths. Very simply, we do some maths. So we do some steps. We apply some stuff that we also know is true. And so it creates like a chain of reasoning, right? We start with something that we know is true, then we do some more stuff that's true, and then we do go from step to step to step, and all the way through, we know every step is correct, so we're all fine. Eventually, we'll then get to the statement that we want. Okay, so we arrive at the statement we want, and the statement we want to prove is true. Okay. And so the idea is that then at every point in our proof, we've done correct steps and correct maths, and therefore then the final statement that we want to prove should also be correct, okay? And that is essentially, that is very simply the whole idea of a mathematical proof. And we will look at ideas again in a moment. And really, mathematical proofs you've done, really, probably even since primary school, really, probably wasn't called a proof, but the idea of one, you've done all throughout primary school and GCSE, and even earlier on in the course. For example, when we proved that two lines are parallel, well, you said to make sure to get the gradients the same, and then if the gradients are the same, then they're parallel. That's a mathematical proof because you use some known facts, and then eventually you got to the fact the gradients are the same, so they're parallel. Sorry. Um, and for example, with equations as well, with simultaneous equations, you substituted them in, or you equated the equations together, and then then you like multiplied both sides. You substituted one equation to another, and that's all correct maths because like equations, you can multiply both sides. For example, 2x is 1. So then you could say 4x is 2. You know, things we take for granted, right? But that's part of a proof, right? That we do some maths, right? We might scale or multiply both sides of an equation by a number, but we know that we can do that, right? That's true. And even for example, back to primary school, right? You maybe would have said that 1 plus 1 is 2. Well, the mathematical fact there is that you can add numbers together to get 2 is 2, right? That's very elementary, but that's the whole idea, right? We apply some maths, right, that we know is correct. We know we can add numbers together in that way, and then we get to this correct statement there. Very simple idea, but you would have done You would the idea of the proof there, you would have done all throughout your school, really, in maths. So there's nothing new here, really. We're again just we're making it more formal, right? We're giving it a sort of an actual name to it, a process behind it. But really, the high rule idea of a proof, we've done, well, really, at GCSE, earlier on in the course. Like I said as well, with parallel lines. You know that two parallel lines are the same if the gradients are equal. So then you found the gradient was equal. So therefore, you arrived at the statement meaning that the lines are parallel, right? So, okay, so that's the idea of a proof then. And what we call this process, this specific process of proving something mathematically, we call this a direct proof. You might see it called, or we call it a proof by deduction. Okay. So, deduction basically means you're basically carrying out a series of steps, right, that you know is logically correct or mathematically correct. So, going from one thing and then you go into another, which is called a deduction, to another, to another, to another, and then eventually you get to what you want to prove, right? Those are what we call deductions, right? Basically, steps, essentially, right? So you get to one fact, then you get to another, then you get to another fact by doing some mathematical steps. Mathematical steps including literally, for example, if we had 2x=1, that could literally mean again times in both sides of an equation by a number. Okay, it can be that is a mathematical step, right? You might take it for granted, but that is a mathematical step. That's a deduction, and so we do a series of steps, again deductions, and in the end we get to the statement that we want. Okay, so you might see it called proof by deduction or something along those lines. And it's also called a direct proof because we are basically addressing the statement head on. We are starting with the fact and then we're doing a series of steps from that fact, right? We're not doing with other types of proof that you'll see throughout the course in the next section and in year 13. We might split into different cases. We might consider some examples, and we might make some assumptions, and so we do some extra steps. However, with this idea of a deductive proof or a direct proof, we literally start from the fact and then we go on from there. Okay. Okay. Another thing we need to look at is the idea of exactly what is a theorem and what is something called a conjecture. Okay. So firstly, we have a theorem, and obviously, you probably would have heard that word thrown around when you did maths at GCSE and in the course. And a theorem, essentially, if we define it now, is essentially just a statement, a mathematical statement that is proven to be true. Okay. So, in terms of mathematics example, it's a statement that we have that there is a mathematical proof that is strong enough to say that it is indeed true for all the values or all the numbers that we want it to be true for. And so some examples, very simply. Again, firstly, going back to GCSE, circle theorems. That's likely where you would have heard the term. So these are properties about circles. For example, when we looked at the circles chapter earlier on, the idea that a tangent is perpendicular to a radius. That's a circle theorem, and that is proven to be true. Okay, there is a proof for that, so we know it is indeed true. And actually, I think it is you would have been expected to know the proofs for that as well. So hopefully, you know indeed that is true. Another example, which we looked at last time, actually, the factor theorem as well. Okay, so the idea that and what we did earlier as well, we looked at if and only if statements. So the double arrow, right? The double arrow being that if we have a factor x minus a, then we also know that x equals a the root. Okay, and that is a theorem that we have proven, right? Mathematicians have proven, and we did actually a little partial proof to that as well last time. Um, we proved that if it's a factor, then x equals a as a root. Okay, so there are proofs behind all of this. Um, so essentially, it's a statement that is proven to be true. Essentially, okay, and we call that a theorem. Okay, if we have proof for it. On the flip side, then we have a conjecture, and again, that is now a statement. Again, a mathematical statement. So we have a statement that is yet to be proven true. Okay, so something that's yet to be proven. So it's something that we think might be true, um, but we don't have a solid mathematical proof to back it up. To prove that it indeed is true. Okay. So for example, and this is a quite famous example, an example called the collapse conjecture, and you don't need to know that. It's just an example. Very very famous conjecture, and it goes like this. It's very simple. Say we have any integer. So if it's odd, okay, any integer could be odd or even. If it's odd, we take that number, multiply by 3, and then add 1. If it's even, we then simply divide by 2. And it because it's even, by definition, it's a multiple of 2, so indeed we can divide by 2. What happens then eventually is every number, any number whatsoever, we pick any number. Well, we think we know it's true, but every example so far, every mathematician has thought of has worked in this case. But if we take any number, any integer, if it's odd or even, doesn't matter. Um, well, what happens is eventually, if we apply these two steps to any number, eventually it will go to 1. Eventually. So, for example, 5. Well, 5 is odd. So, because it's odd by this rule, we multiply by 3. So 5 times 3, and then we add 1. That's 15, add 1, which is 16. Now, 16 then, do with that number now, it's even. So we divide by 2, and that gets us 8. And then 8 is even, so we apply that, and then divide by 2, by that rule. And then we get 4. 4 divided by 2, which is 2, and then 2 divided by 2 gets us 1. And it converges. And it turns out so far, no mathematician has thought of an example that doesn't follow that sort of algorithm that eventually goes to 1 by when you get an odd or an even number. So we think it's true, but despite how simple sort of the problem is, just multiply by 3, add 1 if it's odd, or divide by 2 if it's even. No, not even the top mathematicians ever have come up with a proof for that. So it's created sort of like a fascinating dilemma. Such a simple problem that not even the top mathematicians can sort of come up with a proof for it. You can think of examples, there's tons of examples. You can try yourself, pick any number, follow this algorithm, and then eventually you should get to 1. And if you do get an example that doesn't go to 1, well, actually, we'll get £1 million if you disprove it. Or if you do prove it, if you come up with it, there's £1 million prize, I think. So it's quite a it's very fascinating and very like a famous proof, right? And there is a reward for that as well. But it's just an idea that even the top mathematicians can't come up with a solid mathematical proof for it. And so yeah, so that's a conjecture, right? It's something that we think is true. We can disprove it. We can think of an example to say, well, hang on, it isn't true, so therefore it's not. It can't be proven. But it's yet to be proven. We don't know if it's true or not. So then we need to come up with a proof or find an example that shows it isn't true. Okay, we'll look more about that next time. But those are that's the difference between a theorem and a conjecture. That's the terminology. So I thought I'd go over that here. But yeah, now before we do jump into some examples, there's some notation you need to know, and the first one is these two symbols here, these two arrows. There, and you might have seen them before, but we're going to go over it now. The first one means implies. So what that means is if we have two statements, A and B, that means in this example we would say A. If we said A arrow B, that means A implies B. Right? So that means if A happens, then B happens as well. Automatically, if A is true, then B has to be true as well. Okay? So as an example, if x is positive, x squared is also positive, right? And so actually in using the arrow, we would say if x is positive, that implies, which is what this arrow means, x squared is positive. And we know that's true because, well, 2 squared would be 4. That's positive. And the whole idea, right, is that every square number is positive, right? Because that's how squares work, right? You times it by itself. So if you had a negative number, say negative 2 times negative 2, that will also be positive 4, okay? But if we know x is positive, then that automatically means x squared is also positive. Another example, if n is even, then that implies that n squared is even too. Okay, so then that means if we have a number n and we're given it's even, automatically that implies this n squared is even as well. Again, you can say, well, if n is 2k, remember we can write any even number in the form 2k. Well, n squared would be 2k all squared. That'd be 4k squared, which is 2 lots of 2k squared. So it's a multiple 2, so it's even as well. Okay. So those are some examples. So that means, again, a statement A. So in this case, again, if statement A was if x is positive, so any given number x is positive, then statement B is also true, meaning in this case x squared is positive. Okay, that very simply is how we use that arrow symbol, the implies. Okay, so if we have one statement that is true, then we automatically know another one is true as well. Okay, but what about this double arrow then? That is if and only if. Or we, because we're lazy mathematicians, we sometimes call it if with a double F. Okay, and so we would say A and then double arrow. Oh, bit of a rubbish arrow there. A. There we are, A double arrow B, and that means A if and only if B. So what that is saying is actually in this case it's quite similar to the first one, implies, but it goes both ways, right? So that means if we have a statement A that is true, then that automatically means B is true, like it implies B as well. But it goes the other way around, and also if B implies A. No, if B is true, then that also means A is true as well. So they are sort of equivalent, right? If A happens, then B also happens. And if B happens, then that means A also happens. So they come in basically pairs, right? They're equivalent, right? So we also say A is equivalent to B. So some examples with that then. Well, firstly, we did factor theorem last time, so this would be a relevant example. So if x minus a is a factor, remember, refer back to the factor theorem, then that means if and only if f of a or I should say x equals a is a root, okay? Or we could say f of a equals 0, whatever you prefer. So the idea is that if we have x minus a, we know is a factor of some polynomial, then x equals a is the root of the polynomial. And vice versa, we can go backwards and say if we know x is a is a root of a polynomial, then that also means x minus a is a factor. Okay, they're both equivalent and they're both they both imply each other. Okay, so if one's true, then the other one has to be true as well, no matter which way. Okay, another example: if we have a discriminant which was, say, greater than 0, then that means if and only if there are two real roots, and I'm talking about quadratics here. I should say two distinct real roots. Okay, so we looked at that in the quadratics chapter with discriminants, and we saw if the discriminant was greater than 0 or positive, then that implies that there were two distinct real roots, and we can work back, and that also means as well on the graph, say, that corresponds to two distinct intersections with the x-axis, right? Remember, a root is where it crosses the x-axis. So then we saw if there were, we can go backwards as well and say if there were two distinct real roots, if there were two intersections with the x-axis, then that implies the discriminant of that quadratic has to be positive as well. So again, they both imply each other. Okay, so both one happens and the other must be true as well. Okay, one last example. Let's go back to circles. So if a line is a tangent to a circle, no, I should say a line is a line. So if I have a line that is tangent to a circle, that's if and only if there is one intersection with the circle, between the line and the circle, so remember again, if I draw a little picture, if you have a circle, remember, think back to when we look at circles. If there was only one intersection with a line and a circle, that means it has to be a tangent. Okay, so it touches the circle at that point, and it only crosses the circle at that point only. There's only one intersection. So if we were told a line is a tangent to a circle, that also implies there's only one intersection. Okay, and then we also used, as a result, we can do another if and only if to say that the discriminant then would be equal to 0 if we equated them together, the line and the circle, which we get a quadratic. That quadratic would have a discriminant equal to 0 because it's one real root there. Okay. And it goes the other way as well. And again, if we then found that if we equate a line and a circle and there was one intersection point, then that has to mean the line is a tangent as well. So again, it goes back both ways. Okay, so then what about these examples then? Well, this is only one way because we cannot go the other way. If we're told instead, if we worked on the right side, if x squared is positive, that does not automatically mean that x is positive. Why? Because, well, if x squared is, say, 1, okay, well, we know that's positive, but then x would be plus or minus 1. Remember, we do the plus or minus to solve it, right? So actually, it could be -1. So actually, would not automatically be always positive if x squared is positive. So it only goes one way, okay? You cannot go the other way, okay, in that case. Likewise, with the second one here, n squared is even. If n squared was even, that does not imply that n is even. So you can't do the arrow the other way. Again, because, well, say if n is, 2, very simply. N squared is 2, right? But then n would be, well, plus or minus, but it doesn't really matter about plus or minus here, but plus or minus root 2. Now, root 2 isn't even an integer, it's a third, it's irrational. That irrational and surds don't have even or oddness to it, right? We uh, we just don't classify it as even and odd. We only call things even and odd if they're integers, right? So that means not an integer in this case. If we go the other way, so that's not true. So we cannot go the other way. Nope. So if it's only one way, then it's only implies, okay, and it only goes in one direction, okay. Okay. And the other bit of notation then that we need to know, and actually would have seen this at GCSE, and it's this triple line, and that means identical or an identity. And what that means is it's an expression or a statement that is true for every single value. Okay, so for example, if we have, say, x squared, add 4x, add 3, we can say that is identical to x plus 3, x plus 1. Why? Because it turns out these two, the left-hand side and the right-hand side, are exactly the same for every value of x, okay? Because if we expand this, well, uh, that would get x squared, add 3x, add x up before x, and then add 3 times 1, which is 3. Well, hang on then, the left-hand side is identical to the right hand side because it's a true for every value of x. Okay, so identities, which we represent with this triple line symbol, which means that one side or one expression is exactly identical to the other for every value of x, right? We'll see an example of that in a second. And it's different to an equation, say x squared of 4, let's say x squared add 4x, add 3 equals, say, minus 3. That's different because an equation obviously has two lines. It's a statement that's true, or an expression that's true for only certain values of x, say, right? Because obviously we could solve this equation to get x squared add 4x equals, now I'm going to say 3 here, because then that equals 0, make it simple. Then that turns out it's true. The roots here will be x plus 4 equals 0. And this statement then is only true if x is 0 or x is minus 4. Okay, so it's not an identity. This left-hand side is not identical to 3. Okay, it's only equal to 3 for only certain values of x, and actually only for these two values of x here. So that is the key difference between identity and an equation. Okay, um, the fact that an identity again is true for every value of x. So one side is identical to the other, the left side is identical to the right. However, an equation is only true for certain values of x. Okay, and so yeah, and with identities as well, and we will look at an example in a moment. But the idea is, you might be asked to prove that something is identical to another, and with that, then we prove that the left-hand side is identical to the right-hand side. So in this case example, if we were to prove that both sides are identical, then we kind of need to maybe manipulate or expand or simplify an expression. So in this case, we expanded the bracket and it turned out we get the same quadratic. Okay, we will see more with identities when we look at trigonometry because there's a lot of different formulas we will see there that works for every value, for every angle you can have. Um, and so we'll look more there. But for now, I just want to get used to the notation, right? And so this means an identity, okay, or identical to, okay. So one side is exactly identical to another for every value, okay. So it's not an equation. Okay, cool. Okay, so first example then, we are asked to prove that uh, 3x plus 2, lots of x minus 5, lots of x plus 7 is 3x cubed plus 8x squared minus 101x minus 70. Right, okay. So again, we have this identical symbol. So we need to prove that the left side is identical or exactly the same as the right hand side. Okay, so if I write this out again, 3x cubed plus 8x squared minus 101x minus 70 is identical to 3x plus 2 x minus 5, x plus 7. Now what we need to do is we need to start on one side. Okay, we need to pick a side, and then eventually we can then do some things to then get the other side. And then the idea is to prove that both sides are the same, right? They're done identical. Now to do that, well, we could start maybe from the left. It's a cubic, and then a spot. It should factorize into that, right? So we could use the factor theorem to help us factorize. We need to spot a root or something like that. But I think actually it's a lot simpler. Takes less thinking to do the right side and expand the brackets, and then we should get the cubic. So we're going to start from, and I'm going to say right hand side, okay. And again, I can denote this by using that acronym. You'll be fine to use on the exam. It's a very common sort of abbreviation. But yeah, so we have 3x plus 2, x minus 5, x plus 7. And so we're just going to expand the brackets, and hopefully we get to the other side. So, right. So let's just expand these two first. So if I do that, I get, well, 3x times x is 3x squared. 3x times minus 5 is minus 15x. And plus 2x. And then 2 times minus 5 is minus 10. Lots of x plus 7. And that'd be identical to, and then that's also identical to, well, we can simplify inside the bracket, right? So we get 3x squared minus 15x, and that is a 15, plus 2x is minus 13x, minus 10, lots of x plus 7. That's a bit, let me rewrite that. There we are. So then I need to expand these two brackets again, and then we get, well, 3x squared times x is 3x cubed. 3x squared times 7 is plus 21x. Then minus 13x times x is minus 13x squared. And then minus 13x times 7 is minus 91x. And then minus 10 times x is minus 10x. And minus 10 times 7 is minus 70. Okay, and then I can collect like terms. So we get the x cubed first, 3x cubed. Then for x squared, we have minus 13x squared. Hang on, am I missing an x squared somewhere? Yes, there should be an x squared there. So 21x squared take away 13x squared is plus 8x squared. And then minus 91x minus 10x is minus 101x. And then we have the minus 70. Okay. And let's compare that then. What's the cubic we have on the other side? 3x cubed, 8x squared, minus 101x minus 70 is exactly the same. So there we are then. We then got to the left-hand side. So there we are then. That's our proof done. So therefore we've got the right-hand side is identical to the left-hand side, meaning that this identity is indeed true. And there we are. So you see the idea with this sort of proof, right? We literally start with something we know. In this case, we started from this, the right-hand side. We know we have these brackets. Then we just expanded it. So that's, again, that's a deduction, right? We used our knowledge on expanding brackets and simplifying and collecting like terms. It might seem like fairly basic stuff, but that is, again, math deduction. That's steps, right? And then eventually we did those steps, and then eventually we got to the left-hand side, and that is our proof. So we arrived at the statement that we wanted to prove true. Okay, so there we are. Cool. So let's have a look at this example then. We need to prove that these 3 points A, B, C are vertices of a right-angled triangle. Now, in the previous chapters and we have looked at various examples. Our proving stuff is like a rectangle, square, a parallelogram, a trapezium. So you might be asked to prove a property of a shape, or prove something is a certain shape. And the idea is, the strategy is, firstly, with points, just plot them, right, and see what you're working with. So it's the first thing to do. So we have an axis, x, y. So A is at 1, 1. That's probably going to be a lot there. There we are. And then B is at 3, 3. So that's probably going to be up there somewhere. And C is at 4, 2, so that's probably going to be there somewhere. Okay. And then we can connect all the points together. Oh, and then we should get a triangle. Now we need to prove it's a right angle triangle. And I guess the right angle looks like it'll be there, right? Uh, okay, so that is the diagram. That's what the triangle looks like, but we need to prove it is a right angle triangle. Okay, so there are probably many ways of doing that. One way is, well, you can recognize these as different lines, right? Consider the edges or the sides. And we know that this is the right angle here. It's perpendicular. So the line AB there and the line BC would be perpendicular. So you have to show that it is perpendicular. So you could consider the gradients between the points. They're negative reciprocals, therefore they're perpendicular. It's a right angle, hence it's a right angle triangle. You could do that, but I think probably the safest way, probably the way that is the most sort of consistent, I guess, is Pythagoras theorem, right? Because what applies to right angle triangle? Well, SOHCAHTOA and right Pythagoras, right? And in general, it is a good idea to prove if you need to show something for the right angle triangle, to maybe use Pythagoras theorem. At least when you got all the sides, anyway. In this case. So that's what we're going to do, because then if it obeys Pythagoras theorem, so if a squared plus b squared is c squared, if that is true for the three sides, then that has to be right angle triangle. Okay, every right angle triangle has to obey Pythagoras theorem, and and so if we find with a triangle that you get the three sides and it does obey Pythagoras theorem, and then you know it has to be right angled. Okay, so that's what we're going to do then. So how are we going to get that? Well, we're just then going to find the length of the sides, right? So then the length of the sides. So firstly, AB. Well, again, between points A and B, the length of the distance using the distance formula. That's going to be changing x. So that's going to be 3 take away 1 all squared. Add the change in y squared, which is 3 take away 1 again. And put that in the calculator, you should get 2 root 2. Cool. Okay, then what about another side? Let's do AC. So again, that's going to be the distance between points A and C. So changing x is 4 take away 1 all squared, and changing y is 2 take away 1 all squared. So put that in the calculator, you should get root 10. There we are. And then the last side is BC. Okay. And that's, again, this is also why it's helpful to draw a little diagram of the points and the shape, because you know exactly what to kind of work with. You know what sides we have, and so then it helps you to visualize what you know, how to compute the sides and stuff like that. Anyway, so the distance then between B and C up here. So B and C, again, changing x firstly is going to be 4 take away 3 all squared, and then changing y will be 2 take away 3 all squared. And so that will get me root 2. Okay. Okay, so I've got the sides. So then I need to, well, I need to consider Pythagoras theorem, right? So I need to square all the sides and see what I get. So AB squared then. But AB is 2 root 2, so that's squared. 2 root 2 all squared is 8. And AC squared, well, it's root 10, so that root 10 squared is a 10. And BC squared, um, well, it's root 2, so root 2 squared is just 2. Well, then we can see it's true, right? I can add 8 and 2 and I get 10. So that means AB squared and BC squared, 8 and 2 gets plus 10. So AB squared plus BC squared equals AC squared. Cool. And I'm going to say as 8 add 2 indeed gets us 10. So there we are, that's Pythagoras theorem, right? Two sides squared added gets me the other side squared. Anyway, so therefore, Pythagoras theorem applies. Therefore, uh, the triangle must be right angle. And there we are. So yeah, that is one way, a safe way, I guess, to prove if you need to show a triangle's right angled, just check if Pythagoras theorem applies. Just compute all the lengths, right? You don't have to fiddle with any angles. You don't have to visualize where an angle would be. You just compute the sides, right? It's a safe bet. Again, alternatively, you can consider two lines are perpendicular, and therefore, if they are, has to be a right angle. So you can do it that way as well. But yeah, there we are. And also that means AC would have to be the hypotenuse, the longest side. And we can see that on our diagram because the hypotenuse is opposite or facing the right angle. Okay. As you can see there. There we are. Okay, cool. Okay, this example then. We have the equation kx squared and 3kx plus 2 equals 0, and we are given has no real roots. We then need to prove that k satisfies an inequality. Right, okay. So hopefully you've seen examples like this. I've done examples when we looked at discriminant, and in other chapters the discriminant does come up. So it's really good that you get an idea of how to solve questions like this because it's fairly common. So, why am I saying discriminant? Because it's talking about no real roots, right? So then you should know no real roots means the discriminant is less than zero, it's negative. And it's about that implication thing I talked about earlier, right? No real roots means, well, if and only if. So if that's true, then the discriminant less than zero has to be true as well, and it works the other way around as well. So yeah, we can use the fact it has no real roots, which means the discriminant has to be less than zero, essentially. Okay, so that's what we're going to do then. Let's work out the discriminant here. So that has to be then less than zero, which means that b squared is 3k all squared. Take away 4 lots of a, which is k here, and c, which is 2. And that has to be less than 0. So then we just expand the brackets to then get 9k squared minus 4 times k times 2 is minus 8k is less than 0. Okay, well, at that point, hopefully spotted a quadratic inequality, which we also should be able to solve. We looked at that earlier in the course, and as you see. So the idea is essentially we want to sketch this graph to visualize where it lies below 0, right? So to sketch it, well, we need to solve the roots, right, which we technically call the critical values. Okay, so the critical values are the values of k if we were to solve it. Obviously, we don't have an equation, we have an inequality. But if we were to solve it, we would get 9k squared minus 8k equals 0. So our values, critical values, if we say factorize to solve it, k lots of 9k minus 8, therefore k is 0, or 9k minus 8 equals 0, so 9k equals 8, so then k is 9 over 8 over 9. Okay, and actually we can start to see we get a right answer because our inequality that they want has 0 and 8 over 9, so actually we can kind of almost confirm to ourselves we might be on the right track there. Some assurance there. Anyway, so we've got our values then. That helps us to do a little sketch of this quadratic here. Okay, so obviously you have one root at 0, or critical value at 0, and another root at 8 over 9, say there. And then essentially a graph. Now it's a positive quadratic because so it looks like this, a smiley shape, because the coefficient on the k squared is positive, it's a 9. So with that in mind, it's going to have this sort of shape. Oh, there. Oh, it's a bit wonky, but there we are. You get the gist. So there we are then. Okay, so now I need to look at the inequality. So if it's less than 0, it needs to be below the x-axis, so underneath there. Okay, that is the region we're interested in. So that's going to be between our two critical values, right? So it's going to be between k is 0 and k is 8 over 9. So therefore, we can write our inequality as between 0, less than k, less than 8/9. Okay. K between those values indicates the region there. Okay, cool. So let's check our answer then. Okay, so this inequality, 0, less than or equal to. Right, that's why you check the question. So everything's fine, but interestingly, it says k could be equal to 0 as well. But actually, with this inequality, because it's a strict inequality, that means k has to be strictly above 0, but it could be equal to 0 as well, because again, the question says 0 less than or equal to k. So what we need to then do is basically, in this sort of instance, we then need to check k0 separately. Okay. So when k is equal to 0, let's substitute that in and see what happens then. Right. And then hopefully it should also be 0. But I'll explain why this happens in a minute. But again, so a common strategy then, if this ever happens, if you need to check a particular value for your answer, just substitute that value in and see what happens. Anyway, so k0, then the quadratic, kx squared plus 3kx plus 2 equals 0. If we substitute k0 in, we get that becomes, well, 0x squared is 0. That would go to 0. And the x part will go to 0, okay, because it's k lots. Because it's a multiple k, so it's times by 0. So we're simply left with 2 equals 0, right? Well, hang on, that makes no sense. That's clearly incorrect. 2 is not 0. That means that there are no solutions in this case, right? Because when k is 0, there's no value of x, which gets the equation equal to 0, because we always get 2. Okay, so there's no the equation is not true when k is 0. Okay, but therefore it has no real roots. So no real roots, and I'll say as equation is not true. Again, as simply 2 cannot be 0. No real roots, so therefore 0. K can also be 0 as well, to ensure there's no real roots to the quadratic. So 0 could be less than or equal to k and 8/9, and that is our final inequality. Okay. Now, so that's the answer. That's what a devise an exam situation or something you're unfamiliar with. Just if you ever get an instance like this where you get some sort of inequality or something, and you need to check an additional value, just check it, plug it in, and see what happens. Because then they might need to add that on, just like in this situation. But specifically here, why is 0 not included in this discriminant? Why does that not tell me all the values by just looking at the discriminant? Because specifically when k is 0, if I plug 0 in again, the quadratic goes to 0. Okay. Well, when k is 0, there is no quadratic. There's no quadratic when k is 0. Hence, it wouldn't have a discriminant. So therefore, simply, when we look at the discriminant, it wouldn't include k0, because if it did, then the discriminant wouldn't exist. Okay, so when we can use a discriminant is when there is a quadratic, right? But specifically when k0, the quadratic goes away, hence the discriminant goes away, so it's not included in the discriminant. So we have to check that separately, but includes everything else. Okay. But yeah, very simply, that's why k0 is missed out from there. But as again, just check an additional value if you get in that sort of situation. But there we are. Okay, let's have a look at some further exercises, and I'm going to start with exam question first before we look at the actual exercises, because it's a bit easier than the exercises, and it's a very important one, so I'd want to go over it first. Very typical exam question this is as well, and it says show that x squared minus 8x plus 17 is greater than 0 or above 0 for all real values of x. Okay, so this is almost hinting like an identity. It's true for every value of x. But yeah. But anyway, we need to show that this quadratic expression is always above 0, greater than 0. Okay. So there are probably many ways of proving this, but I think again probably the most common one, maybe the safest one, in the sense that it probably works most of the time, is, well, let's think about it. If we know every quadratic has to have a minimum point, if it well we know it has this sort of shape, right? So it have a minimum point down there. So we know every quadratic will have a minimum. Well, what that means is then, what if the minimum value of this expression, if that is above 0, then surely everything else is as well, because the minimum value is the smallest value, right? If the smallest value is above 0, then so does everything else. Okay, so then we need to investigate that. But how do we get the minimum value? Hopefully, you're screaming quadratic complete the square. Sorry, complete the square, right? So the complete the square will help us here. If we then take x squared minus 8x plus 17, we can prove stuff like this by using complete the square, and that'd be identical to, well, if you complete the square on this, it'd be x, and then a half of minus 8 is minus 4, all squared. Take away 4 squared, which is 16, take away 16, and then add 17, and we can simplify it to x minus 4 squared plus 1. And why is it an identity again? Well, it's not an equation because both sides are true for every value of x. Okay, so it's an identity in that case. Okay, because two expressions on either side are exactly the same, no matter what. Anyway, there we are. So we got it to complete the square. Right, again then, well, if this is a square number, right? It's something squared. Yes, it has an x in, but it doesn't matter. Everything in the bracket is squared. So that means this whole thing, then, this bracket has to be at least 0, right? Okay, well, if that's at least 0, then if we add 1 no matter what, but then overall, it'd be above 1. So therefore, the whole thing has to be at least 1. Okay? And then if it's at least 1, well, then we know it has to be above 0, because simply 1 is greater than 0. Okay? And so to justify this, to write it down, to get all the marks, right, to be thorough, well, we're going to write down what I just said, right? The square has to be above 0. So I'm going to say x minus 4 squared has to be above 0, as it's a square number, but you don't need to write it necessarily. So if that's above 0, then if we add 1, has to be above 1, right? So therefore then, that's also above 0, so then we can simply say that the quadratic plus 17 has to be above 0, and there we are. That's our 4 marks. Cool, and so yeah, and just to explain again, that's an identity, obviously, as both sides of the equation or the identity, sorry, are exactly the same. You can check this if you were to then expand the bracket, and then you get back the quadratic, because remember, we can write a quadratic in completed square form, and they're both equivalent, right? They're both identically the same. But yeah, so there we are. Cool. And so again, lastly, to touch, again, this comes up often-ish in exams, so it's useful to know with this type of question, if you want to consider the minimum or the maximum value of a polynomial of a quadratic, you complete the square will be very helpful for these type of questions, because that's what the completed square does. It tells you the minimum or the maximum value of a quadratic. Okay, so let's move on. Okay, we have this example. We need to prove that this line 4y minus 3x plus 26 equals 0 is a tangent to the circle x plus 4 all squared plus y minus 3 all squared is equal to 100. Now, again, we looked at examples like this in the circles chapter, last chapter. And so, if this line is a tangent to the circle, what that means is, if it's a tangent, that means there's only one intersection between the line and the circle. Okay, okay. So then we're talking about intersections then. So we're going to need to equate them together. Okay. So we need to substitute the one equation to the other. It's best to rearrange the line, right? So if we first call this equation 1 and 2, again, because they're simultaneous equations effectively, if we substitute one into the other, let's rearrange the top one then to substitute. I'm going to rearrange for x, I think. It's probably a bit easiest because then we can add 3x to both sides to get 3x. Now I'm going to write it down here. 3x is equal to 4y add 26. Therefore, x, then if we divide by 3, it's 4/3 y. Add 26 over 3. Now, I can't simplify this fraction, sadly. So we just have to deal with some fractions. But yeah, that's rearranged. So I can substitute that x then into the second equation, into the equation of the circle. So I'm going to say sub x into 2. And here we go. So firstly, we have x plus 4 squared, where x is 4/3. Oh, y plus 26 over 3. And then we add 4, all squared. Now, we can simplify that actually, because 26 over 3 add 4 is 38 over 3. There we are. Cool. And then we had, what was it? Y minus 3 squared. Okay, that's just y minus 3 squared. And I'm going to move the 100 to the other side. So take away 100, and then that's equal to 0, just to get the equation, right? There we are. So then we need to expand the brackets. So this one first, well, this one's quite awkward. What you could do to help yourself is literally that first bracket, 4/3 y 28 over 3. Do it aside somewhere on the page, right? And then you can, and that's 38, right? And then you can expand it term by term if that makes it easier, because it can be quite easy to do a misstep in the algebra there. It's quite intricate algebra here. But if you do that, well, then, well, you're going to get 4/3 y times 4/3 y again. So that'd be 16 over 9 y squared. Then you're going to get 4/3 y times 38 over 3. And then that would be 152 over 9y, but there'd be another lots of that, double that. Then, so that would be 304. So add 304 over 9y there, and then we're going to get 38 over 9 over 3, sorry, all squared. So 38 over 3 times by 38 over 3 again. You're going to get 1444 over 9. Okay, and then, okay, that's dealt with. Then we expand this bracket. But that's a lot easier, hopefully, thankfully. No fractions. So y times y be y squared. Y times minus 3 is minus 3y. Another minus 3y with minus 6y. And then minus 3 times itself. So plus 9. And then we have take away 100 equals 0. Okay, so you'll get that eventually if you expand the brackets. Again, you could do the brackets somewhere else and do it, take your time with it, if it, because the algebra can be quite brutal here. But there we are, we get that. Now, at this point, you can add the terms, collect like terms, simplify it, but I can actually get rid of the fractions to help me with that, to make it a lot easier to read and more presentable. If I just times both sides of the equation by 9, I get rid of all the fractions, right? So then I get 16y squared, add 304y, add 144, 4. And then y squared times 9 is 9y squared. Then 9 times 6 is minus 54y. And then 9 times 9 is plus 81. And then minus 100 times 9 is minus 900 equals 0. There we are. It's a lot nicer to work with now. Then we can add, then we can collect the like terms. So 16y squared, 9y squared be 25y squared. Then 304y. Then we have minus 54y. That would be plus 250y. And then lastly, the numbers 1444, add 81, take away 900. That's going to get me plus 625. And then that will equal 0. So there we are, we've got a quadratic. Actually, we can even simplify that because it turns out 25. goes into all the terms, right? 25y squared over 25 is just y squared. Then 250 divided by 25 is plus 10, so 10y. Then 625 divided by 25 is 25, so add 25 equals 0. There we are. Very, very nice quadratic here. So we can't do anything more with it. We can solve it, but do we need to? Because the question only says prove that it's a tangent. Now, we need to show that that means there's only one intersection. How else can we show that? Well, you could show there's only one point, right? You could perhaps solve it if you wanted to, and you'd get only one point of intersection. You could. But to save the bother, well, we also know intersections and solutions, right? One solution. That also means the discriminant has to be equal to 0, because that means there's only one real root, right? Which means one intersection. Okay, so what we could then also do simply is just do the discriminant of this, right? Again, that should be a fairly common sort of tactic with these type of questions. We've seen them before. So if we consider the discriminant, right? If we calculate the discriminant, hopefully we get 0. So the discriminant here will be, well, 10 all squared. Take away 4 lots of A, which is 1, C, which is 25. So then that would be, if we put that in the calculator, 10 squared, take away 4 lots of 25. That indeed gets you 0. Okay, there we are. So therefore, discriminant equals 0, which therefore means there is only one intersection, right, between line and circle. And ultimately there, because there's one intersection, means the line must be a tangent. And there we are. Cool. There we are. Nice. So again, you see with the chain of reason, again, this is what we call a deductive proof by deduction. We did some maths, right? We carried out some steps, and then we have this deductive reasoning at the end, right? We did some lot of we had this chain of reasoning, right? Which ultimately proved that the line has to be a tangent. There we are. Cool. Okay, last question then. A very similar one again. And we are given a circle with equation x minus 1 all squared and y squared is equal to k. And we're given a straight line L, which is y is ax. And we're told it cuts the circle at two distinct points. Again, then, it's talking about intersections. If it's two distinct points, I'm thinking the discriminant, right? That might help. If it's two distinct points and two distinct roots, real roots, well, that means the discriminant has to be above 0 or positive there. So I'm going to note that then. That might come into help because that's what you usually do with these questions. But okay, we then need to prove this inequality here. Okay, so yeah, so that's going to make sense then, because this is an inequality. So that kind of hints that I'm going to need to use that to get this answer. So again, this looks scary, right? This is why I picked it actually, because it looks like a scary question right off the bat. Like, what is this weird inequality? But really, once you, we will go through it now. But you know, if you do the normal steps, you know, what we're going to do first, right? Is talking about intersections, so we're going to equate them together, and eventually, then you'll see it's fair if you do like the normal steps. It's not too bad. Anyway, let's do it. So it's talking about distinct points at intersections. So we're going to equate them together. If we call, so these are like simultaneous equations again. I'm going to substitute the second one, so y, into the first equation, the circle. If we do that, we get well, x minus 1 all squared add y squared. Now y is ax, that'd be ax all squared. And then I'm going to take away k to both sides and make it equal to 0 to get an equation. Okay, then I just need to expand it. So if I expand it, I get x squared. Take away x, take away another x will be 2x. And then minus 1 all squared is plus 1. And then we expand this, so then that would be plus a squared x squared. And then take away k equals 0. Okay, now it's probably helpful to rearrange it exactly into a quadratic. So if I collect all the x squared terms firstly, I would get x squared and ax squared. So that'd be 1 plus a squared, lots of x squared. If I factorise, then I have minus 2x there. And then lastly, I have 1 minus k, the numbers, right, with nothing attached to x, and that's equal to 0. There we are. So now that's in a quadratic form quite nicely. So at that point now, that's where this discriminant's going to help us, because now we can consider the discriminant, because again, if it's two distinct points, that implies, remember use the arrow we use, that also then implies that the discriminant has to be above 0. So that has to be true. Okay, there we are. So therefore the discriminant has to be less than 0, no, above 0, sorry. Yep, okay. So if it's above 0, then if we compute the discriminant here, so b squared is just minus 2 all squared, minus 4 lots of a, which is this coefficient here, 1 plus a squared, lots of c, which is 1 minus k, and that's to be above 0. Cool, then we just expand it. So minus 2 all squared be plus 4, take away 4, then I'm going to 4, and then I'm going to expand these two brackets first, right? So 1 plus a squared, lots of 1 minus k. So firstly, 1 times 1 is 1, 1 times minus k is minus k, a squared times 1 is just a squared, and a squared times minus k is minus a squared k. And that's greater than 0. Then I need to expand by times it by minus 4 outside. So then that before take away 4 times minus k is plus 4k, minus 4 times a squared minus 4a squared, minus 4 times minus a squared k is plus 4a squared k, above 0. And actually we can simplify this because these 4's cancel out here, and we're left with 4k minus 4a squared plus 4a squared k is greater than 0. And actually, we can also then divide both sides by 4, actually, to simplify it even further. And it doesn't change the inequality, because we divided by a positive number, remember. If it was minus 4, say, then we'd have to reverse the inequality. Remember, dividing or multiplying both sides by a negative number would affect the inequality, but because it's positive, it doesn't matter here. So that would simply go to k minus a squared plus a squared k greater than 0. Okay, so we got to that point. What do we do then? So again, we then star our answer, and we see it's k has to be greater than this fraction of a, right? It looks a bit weird, but it's just k. It looks like k in terms of a, right? It looks like it's rearranged for k on one side. So that's what we're going to do, essentially, and hopefully then we get that inequality. We're going to somehow get k on one side on its own, almost like rearranging for k. So, well, that's what we need to do. So first, we get this a squared to the other side. That's not attached to a k. So that'd be greater than a squared if we add a squared to both sides. Then I can actually factorize out a k, and then that'd be 1 plus a squared is greater than a squared. And then to get k, well, then we just divide by 1 plus a squared to get a squared over 1 plus a squared. And there we are. That's that inequality. And again, to note, when we divide by 1 plus a squared, we're allowed to do that because, again, it won't affect the inequality direction because that's a positive quantity. Because a squared is a square number, that's positive, and adding 1 will make it positive. So the inequality is fine. Anyway, there's the answer then. Cool. So again, hopefully you see that wasn't too bad, right? If you've done questions like this before, it's the same method, right? You substituted it in using the discriminant, and then therefore we get our answer. It looks scary at first glance, but really, if you do the same sort of thing, it's not too bad, right? Hopefully, at least to me, it's not too bad anyway. But yeah. So that's so again, hopefully you start to get an idea now. Again, like these questions are the proofs, right? We're proving stuff, but really, you probably would have done questions like this, all throughout the course. We just, it's just it's technically called a mathematical proof, right? The idea of proving certain statements. Using, in this case, again, in this section, the idea of we go from one step to another, make sure all steps are mathematically correct, right? So make sure we expand brackets the right way or multiply if we multiply both sides of an equation, do we make sure we actually multiply every term by the same number? Stuff like that, making sure we don't make any mistakes, essentially, right? So then the idea is to start from something that we know we're given, right? Something we're given. Then we do some steps, and eventually we get to our answer. Because then the idea is if we've done everything correct, then our answer should be the correct, which means we've proved it successfully, like in this example here. And so that's the idea of mathematical proof, right? Again, I don't think really anything new, I would really say, apart from some new terminology and some notation at the start. But really, the whole idea of these questions shouldn't be anything new. Um, you would have seen questions like this earlier on in the course. And indeed we'll see more later on as well. But next time we're going to look at actual types of proof, which I think is a bit harder. There are different ways or different techniques we can prove certain statements that are not necessarily easy to prove if you just take it head on. Okay, so we might need some different methods, but we'll go over that next time. But for now, that's the idea of a mathematical proof. So yeah, I'll see you next time.